Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 13, Part 3, Model Building and Diagnostics, Transformations. All right. If we find the correct functional form between our x's and our y's, then the plot of our xi, ei pairs should be centered around 0. Whenever we make our transformation, we're going to include the main effect in the model. So for example, if I'm going to use xi squared, I'm going to keep the xi in the model, right? So what we are going to do is once you get each of your x's, let's call this x1 and your residuals. For each of those x's, you're going to check if your residuals are random around 0. Okay. If you see a pattern in your plot, then that's going to give you some indication that you're going to need a transformation. All right. Another thing you could check is the relationship between your standard deviation and your mean, right? So essentially, if the spread is proportional to the square root of the mean, then a square root y transformation might be appropriate. If the spread is proportional to the mean, then a log y transformation might be appropriate. And if the spread is proportional to the mean squared, a 1 over y transformation might be easy to use. Sometimes it's really just about trial and error. You're going to try different transformations, then look at your residual plots, and then go back and maybe edit your transformations. Another option is to use some sort of methodology to determine the best functional form for a transformation. We're not going to cover that in this class. We're going to just use some few generic transformations and do the best that we can. Future classes might go into like a Box-Cox method or some other methodology. All right, here's an example where we have x and log of x, and you could see if you saw this sort of pattern in your scatter plot, right? If your data looks something like this, then a log transformation might be useful. If your data looks more scattered in this way, then you could get that 1 over x would give you this shape. If your data looks like a parabola, then an x squared transformation might be appropriate. If your data looks like a cubic, then a cube transformation. And if it looks like a square, then this is an example of what when a square transformation might be appropriate. All right. As an example, we could look at the latitude longitude data set on this website. We have January temperatures as our response variable. We have the latitude as well as the longitude. So we're thinking, if we know where we are based on latitude and longitude, could we predict January temperature? And we can see that latitude with January temperature, right, has this negative relationship. If you look at longitude with January temperature, maybe a cubic might be fitting this a little better. And so if we fit a model with just the main effects, latitude and longitude, we can get our estimates, right? So we'd get y hat equals 98.65 minus 2.16 times latitude plus 0.13 times longitude, right? And we have a fairly good adjusted R-squared value, 0.7314. But when we look at our residual plots, we see that we might have some issues. So here, maybe we need a square term for latitude based on the shape of the residuals. And for longitude, once again, we see maybe we need a cubic term. So we can fit the following model where we say we have our main effect for latitude, but then we also put in latitude squared. And for longitude, we have our main effect for longitude, but we also add in longitude squared and longitude cubed. Okay, so doing this in R, we can fit our model as we did here. So we still use LM for the linear regression model, but now we say, let Y follow latitude plus an indicator function of latitude squared, and then longitude, indicator function, longitude squared, indicator function, longitude cubed. And we get this final model here. So our new model will be Y hat equals negative 0.07. I apologize, wrong direction. Negative 729, right? We're moving that decimal to the right 2 places. Minus 4.91. Times latitude. Plus 0.034 times latitude squared. Plus 30.69 longitude. Minus 0.3453 longitude squared, right? And plus 0.00127 times longitude cubed. All right, so then if we know the latitude and longitude, we could predict the January temperature. So when we look at the residual plots of our new model, they look much more random. They're maybe not perfect, but it looks a lot better than our residual plots, right? This was model 1 residual plots. And then here's our model 2 residual plots. So overall, by adding the squared term for latitude, and then adding the square term for longitude and the cube term for longitude, we get a much better model in terms of our residual plots. And also notice that this adjusted R-squared value has also increased because our predictive power has increased. So if we look at those 2 models back to back, overall you would choose model 2 over model 1 based on your residual plots as well as your adjusted R-squared.